Hello, everyone, and welcome to Conf42's DevOps 2026. I am Srinivas Pagadala Sekar, and thank you for joining me today. I'm excited to share with you a topic that has become increasingly critical in our industry as we navigate the complexity of modern software delivery. Today, we are going to explore how GitOps, observability, and artificial intelligence converge to create resilient systems that automatically detect and recover from failures, significantly reducing downtime and minimizing the need for human intervention. So, this isn't just about automation for automation's sake. It's about fundamentally transforming how we think about reliability and resilience in our CI/CD pipelines, moving from reactive posture to a truly proactive one where our systems can heal themselves before problems impact our users. So, let me tell you a small story. Let's picture yourself as a platform operations engineer, and it's about 3 a.m. in the morning. Your phone buzzes, and you get alerted another deployment has gone sideways. You scramble out of your bed, open up your laptop, and start the familiar archaeology. So you started to wonder, like, what changed, who deployed what, where was the drift, and honestly, this was my life for years. And I know many of you have been there too. Today, I want to show you how we can write a different ending to that story. So, before we dive into the technical content, let me take a moment to introduce myself and share a bit about my background. I currently serve as a senior site reliability manager, and I have been fortunate to spend over 15 years working across various domains in our industry. I have played roles as a DevOps engineer, cloud infrastructure designer, platform engineer, and a cloud native tech as well. So, throughout this journey, I have worked on building resilient Kubernetes platforms by implementing GitOps practices at scale, working with organizations that span multiple industries, including retail finance, banking, and technology modernization initiatives. So, what truly drives me is the passion for transforming how organizations deploy and manage software in production environments and helping teams to move more fragile manual processes to robust automated systems that can withstand the pressure of modern business. When I'm not immersed in platform engineering or writing pipelines, I love following autosports and I explore a lot into the fascinating world of autonomous automotive engineering and innovation, which increasingly shares my parallels with the self healing systems that we will be discussing today. So, let me start by painting a picture of the critical challenge that we face today, because understanding the problem deeply is essential to appreciate the solution that we are going to explore. The statistics here are quite sobering, and they represent a real pain that many of you have likely experienced firsthand. When we look at the production incidents across the industry, we find that approximately 70% of them are caused by deployment failures using traditional CI/CD pipelines. Think about that for a moment. Nearly three quarters of the issues that wake up your on call engineers in the middle of the night aren't due to infrastructure failures or external factors. So they are caused by the very process we use to deliver value to our customers. Even more concerning is that the average mean time to recovery for failed deployments without automation typically ranges from 2 to 4 hours, which in today's world represents not just the revenue lost, but eroded customer trust and competitiveness. So, the fundamental difference between traditional CI/CD and what we are calling modern platform comes down to one word: it's the technical posture. Traditional approaches are inherently reactive, where teams scramble to fix issues only after they have already broken in production. This creates a cascading series of problems where manual interventions create delays due to human errors, or the problems that compound to initial problems and pile up over time, which increases the incident fatigue and also degrades the team's performance and morale. So, in contrast, modern platforms take a proactive approach where self healing systems detect and resolve issues automatically. So, this isn't about replacing human intelligence, it is about augmenting it, allowing our engineers to focus on innovation rather than fighting fires. Through intelligent automation, we can reduce toil, minimize downtime, and maintain reliability at scale in ways that were simply impossible with the manual processes. This brings us to the critical question that will frame our entire discussion today. So, how do we move from what I call is deploy and pray to deploy with confidence? So, how do we build the systems that are resilient by design, that can detect problems early, and that can take corrective action faster than any human operator could? So, that's exactly what we are going to explore today. So, in today's session, it is designed in a way to give you both a conceptual framework and a practical insights needed to architect resilient CI/CD pipelines using Tekton and ArgoCD that can truly heal themselves when problems occur. So we are going to present a GitOps native approach to self-healing deployments that stands on three powerful pillars, each essential to the overall architecture. The first pillar is observability, which provides real time visibility into our system's health, performance metrics, and deployment status across the entire platform. So you simply cannot heal what you cannot see. And the comprehensive observability is the key foundation upon which all the self-healing capabilities are built. So we need to know not just that something is wrong, but we need to know what is wrong and how severe it is and what the broader context looks like. The second pillar is the automation, which eliminates the manual toil and human error through intelligent, policy driven deployment processes and recovery mechanisms. So, this goes beyond simple scripts. When we are talking about sophisticated automation that can make nuanced decisions based on multiple signals and which can execute complex recovery procedures and also maintain detailed audit trails for every action taken. So, the third pillar is the AI integration, where machine learning powered decision making is done from the patterns in your specific environment and it optimizes reliability at scale over time. So, this is where the system evolves from simply responding to known failure modes to predicting and preventing issues that haven't even occurred yet. So, our overarching goal today is to show you how to drive reliability at scale across modern Kubernetes platforms while maintaining the development velocity and reducing the operational overhead. So, these aren't just competing concerns, they are synergistic when approached correctly. And that's the paradigm shift that we are aiming for. So let me walk you through the roadmap for our session today so you know what to expect and can see how each piece builds upon the previous one. We will begin with the GitOps fundamentals, exploring why GitOps provides the essential foundation for resilient deployments and why you cannot build truly self-healing systems without this declarative Git-centric approach. From there, we will move into resilience patterns, examining the key use cases and the real world scenarios where self healing mechanisms prevent outages before impact the users. Next, we will take a deep dive into self healing architecture, unpacking exactly how deployments can automatically detect problems and fix themselves without human intervention. So, to ground this in reality, we will then examine an airline industry case study, learning from mission critical systems where downtime is quite literally isn't an option and where the stakes couldn't be higher. Following that, we will explore AI integration in depth, discussing how to implement intelligent automation throughout your CI/CD pipeline practical and in a more achievable way. We will then talk through the high level flow of the complete architecture of self healing deployments, ensuring you understand how all the pieces fit together into a cohesive system. Finally, we will conclude with the best practices and the key takeaways, giving you actionable strategies that you can begin implementing immediately in your organization, regardless of where you are currently in your current DevOps maturity journey. So let's establish our foundation by understanding what GitOps really is, because there is often confusion about this particular term. GitOps is a way of implementing continuous deployment for cloud native applications that focuses on a developer centric experience when operating infrastructure. So fundamentally, it means using tools that developers are already familiar with, particularly Git, and continuous deployment tools to manage not just the application code, but the infrastructure and the configuration as well. So there are four core principles that define GitOps, and understanding these is very crucial to everything else that we will discuss. First, it serves as the single source of truth for everything in your environment. So this means infrastructure definitions, application configurations, and policies and other configs are all defined declaratively in version control, providing a complete audit trail and change history. So when someone asks who changed what and when, Git gives you the answer instantly and immutably. So GitOps relies on declarative configuration rather than imperative commands. So you describe your desired state, not the steps to get there, but the system automatically figures out how to achieve that state and maintains it continuously. So this is a profound shift from traditional operations where we execute sequence of commands and hope they work correctly in order. Third is the automated reconciliation that ensures continuous synchronization between your Git repositories and your cluster, guaranteeing that the actual state always matches the desired state. So this isn't a one-time deployment. It is a continuous process where drift is detected and corrected automatically, maintaining consistency without manual intervention. And finally, everything is observable and auditable. So you have complete visibility into what changed, when they changed it, and why that particular change was made. So every modification is tracked, reviewed through a standard development practice like pull request, and most importantly and completely, it is reversible. And now, why does GitOps matter specifically for resilience? So there are several compelling reasons for that. First, it provides instant rollback capability, meaning any deployment can be rolled back immediately with a simple git revert, and no complex procedures or lengthy runbooks are required. Second, you get built-in change management where every change goes through a peer review via pull request, ensuring quality and knowledge sharing before anything reaches production. And the automatic drift detection means that manual changes or configuration drift are identified immediately, preventing those frustrations like, hey, it worked yesterday scenarios that plague pretty much the operations team when someone makes an undocumented change directly into the cluster. So GitOps eliminates this entire category of problems by making it impossible for the cluster state to deviate from Git without being detected and corrected. Now that we understand GitOps conceptually, let's look at the specific cloud native stack that implements these principles in practice. The architecture consists of four key components that work together seamlessly. So at the foundation, we have our Git repository, which serves as the source of truth. This repository contains application code, infrastructure definitions, and Kubernetes manifest that describes everything about your desired system state. So this isn't just storing files in Git. It is treating Git as the authoritative of how your entire system should look like and behave. Next, we have our CI pipeline, which in our case is implemented using Tekton. So Tekton is a cloud native solution that everybody is aware about, which handles the building, testing, and security scanning, stamping of images, and image promotion workflows. What makes Tekton particularly powerful is that the pipelines themselves are defined as native Kubernetes resources, meaning they follow the same declarative patterns and benefit from the same operational practices similar to your applications. So the CI pipeline is responsible for taking code from developers, validating it thoroughly, and producing artifacts that are ready for deployment. Then comes the CD controller implemented with ArgoCD. This is where the magic of continuous reconciliation happens. ArgoCD continuously monitors your cluster state, compares it against the desired state in Git, detects any drift that occurs, and enables automated rollback when health checks fail. So this isn't just a deployment tool. It is an active reconciliation engine that always works in the background to ensure that your cluster matches your Git repository, which will internally depict your desired state. Finally, we have the Kubernetes cluster itself, where applications actually run. This cluster has an integrated observability stack that is built along with it. So that can include various tools like Prometheus for metrics, Grafana for visualization, and OpenTelemetry for distributed tracing. So these tools provide the real-time insights that enable self-healing capabilities, feeding information back to ArgoCD and other components so they can make intelligent decisions about the health and behavior of your applications. So let me walk you through some real world use cases that illustrate the power of GitOps in practice, because these scenarios represent problems that many of you are dealing with right now. Understanding how GitOps solves these specific challenges will help you see where you might apply these patterns in your own environments. The first use case is an automatic rollback on health failures. So imagine a scenario where a new deployment introduces a subtle memory leak, and that isn't caught during testing. So in a traditional environment, this plays out painfully. The deployment goes out, memory usage gradually climbs, the application eventually becomes unresponsive, and the ops team gets paged about it, and they will have to diagnose the issue, identify which deployment caused it, and then manually roll back. So on the onset, like, this entire process typically takes around 30 minutes or more, during which your users are experiencing degraded service or even outages. With GitOps, ArgoCD is continuously monitoring the health of your applications against defined thresholds. So when it detects the degradation pattern, it automatically initiates a rollback to the last known good version in under 2 minutes. How good is that? So often before users even notice that there was an issue, the system heals itself faster than any operator could respond. The second use case can address configuration drift detection. Picture the scenario where someone on the team needs to make a quick fix in production, maybe adjusting a config map to change a connection timeout. They make the change directly in the cluster with kubectl because it's urgent, and then they fully intend to update the Git repository later. But when they get pulled into something else and forget, it is as equivalent to the situation in a traditional environment. So in a traditional environment, this drift goes unnoticed until the next deployment cycle, when suddenly things break because the deployment overwrites that manual change that was made by the ops team, and nobody remembers what was changed or why it was changed. With GitOps, this manual config map change is detected within seconds because ArgoCD sees that the cluster state has no longer matches your Git repo. It can either alert the teams immediately, or depending on your policies or your settings, automatically Argo can reconcile back to the Git state, ensuring that all change flows through your proper change management process. So the third use case tackles multi-environment consistency. Addressing that classic term works on my mission syndrome that has plagued our industry for decades. I hope you all agree with me on this. You have all experienced the scenario where something works perfectly in development but fails mysteriously in production. Often this happens because the environments aren't truly identical. There are subtle configuration differences, different versions of dependencies, and manual changes that were made in one environment but not the others. With GitOps, the same Git commit is promoted through environments, ensuring predictable behavior. So your production deployment is using exactly the same configuration and manifest that worked in staging, eliminating an entire class of environment-related failures. So let me continue with 3 more use cases that demonstrate the breadth of problems that self-healing GitOps systems can address. So these scenarios go deeper into the kinds of runtime issues that are particularly challenging to handle manually. The fourth use case specifically, which involves a dependency failure handling, like when a database connection pool becomes exhausted. So this is particularly not a good scenario because it often happens gradually under load. When new requests start failing because they can't get the database connections, error rates climb up, but the application pods themselves appear healthy because they are not crashing. They are just unable to serve the request properly. In a traditional setup, by the time someone notices and starts investigating, you might have already lost ground on a lot of significant traffic and customer transactions. With ArgoCD monitoring, not just pod health, but application level metrics like error rates and response times can be helpful in detecting this degradation pattern and automatically rolling back to the previous version while simultaneously alerting the team about the issue. So the system recognizes that something about the new deployment is causing a problem with the database connectivity, and it takes a corrective action immediately. In the fifth use case, we examine like the canary deployment failures, which represent a more sophisticated failure mode. So you have deployed a new version using a canary strategy, initially routing just a small percentage of your traffic to the new version while keeping most traffic on the stable version. During the canary phase, you detect elevated error rates or increased latency in the new version. So in a traditional setup, someone has to be actively monitoring these metrics and have to make a decision about whether the difference is significant and manually halt the rollout. So this might require constant human attention and introduces the risk of missing the signal in the noise. With GitOps and proper health checks integrated into your canary analysis, the system automatically halts promotion when the canary version shows degradation compared to the baseline. When the traffic stays on the stable version, an alert is sent to the team, which with the detailed metrics about what went wrong, and the problematic version never reaches full production in this case. So here we are preventing a situation where what could have been a major incident. The sixth use case deals with the network partition recovery, which is particularly relevant for distributed systems running across multiple clusters or availability zones. Imagine a scenario where a network partition temporarily isolates a part of your infrastructure. During this partition, some automated processes or operator might take changes trying to compensate for what appears to be a failed node. When the partition heals, you suddenly have inconsistent state across your infrastructure. So traditional systems can get into very confused states during these scenarios, requiring manual intervention to reconcile the differences. With GitOps, once the partition heals, ArgoCD recognizes that certain parts of the infrastructure have been drifted from the desired state in Git and automatically reconciles them, bringing everything back into alignment without human intervention. So the system recovers from partition automatically because it always has Git as the authoritative source of truth that it can return to. So now let's examine the architecture of self-healing deployments at a deeper level, understanding how the various layers work together to create resilient systems. In this architecture is built with four distinct layers, each with specific responsibilities that contribute to the overall self-healing capability. The first layer is observability, which serves as the sensory system for your platform. This includes metrics collection through Prometheus, log aggregation through Loki, or the Elk stack, and also distributed traces using Aegir or Tempo. Together, these tools provide comprehensive system visibility, allowing you to understand not just what is happening right now, but also the historical patterns and the context around that event. Without rich observability, self-healing is impossible because the system has no way that it can detect a problem or verify the remediation action that actually worked. The second layer is the analysis engine, which takes all the observability data and makes sense of it. This includes health checks performed by ArgoCD, the SLO and the SLI monitoring metrics that compares actual performance against defined objectives, and anomaly detection algorithms that can identify unusual patterns that might indicate problems. This layer is responsible for identifying issues before they escalate into full blown outages, giving the system time to take preventive action rather than reaching or reacting to failures. So the third layer is the decision and the action layer, where the system actually responds to detected problems. So this includes auto rollback capabilities through Argo rollouts, auto scaling through horizontal pod autoscalers or vertical pod autoscalers, or even using a Kubernetes event-driven autoscalers too, which is otherwise called as KIDA. These tools can be used and helpful for more sophisticated event-driven scaling. And for traffic shifting, we can leverage service measures like Istio or Linkerd. This layer embodies the self-healing capabilities, taking concrete actions to resolve issues automatically based on the analysis from the previous layer. The fourth and the final layer is the GitOps reconciliation, which closes the loop by updating Git with any remediation actions that were taken, creating a complete audit trail of what happened and why it happened. So this layer also handles notifications to the teams, ensuring that while the system is healing itself automatically, humans remain informed and can intervene if required. This creates a perfect balance between automation and human oversight, where routine issues are handled automatically, but the team always has visibility and the ability to make manual control when needed. Let me show you what self-healing mechanisms look like in practice by walking through a specific example of health-based auto rollback with a progressive traffic shifting will look like. So this will help you understand the detailed mechanics of how these systems operate in real deployment scenarios. Argo Rollout is a powerful tool that extends Kubernetes deployments with advanced deployment strategies like Canary and Blue-Green. And what makes it particularly valuable for self-healing is its ability to monitor Canary deployments with progressive traffic shifting and automatically rolling back when health checks fail. So here is how this works in practice. So you start by routing just 5% of your traffic to the new version while keeping 95% on the stable version. So during this initial phase, the system is closely monitoring three categories of metrics: error rates to see if the new version is generating more errors than the baseline, latency measurements that can to detect if response times have degraded, and resource usage patterns to identify if the new version is consuming more memory or CPU than expected. In any of these metrics exceed defined thresholds, the rollout is automatically halted. The system doesn't wait for a complete failure. It detects degradation early and stops the promotion process before the problematic version can impact more users. If the canary phase looks healthy, traffic is gradually increased, perhaps to 10%, then to 20%, and then to 50% with all the health checks at each stage of it. This progressive approach means that even if a problem only manifests under higher load, you can catch it before it affects your entire user base. So looking at the sample code on this slide, you can see how this is configured in practice. So we define a rollout resource that specifies canary strategy with multiple steps. Each steps can set terrific traffic weight, pause for a duration to collect the metrics, and run analysis templates that define the health checks. The analysis template references Prometheus queries that check your success rate against defined thresholds. So the crucial configuration here is the auto promotion enable, which is set to false, which means that the system won't automatically proceed to the next step unless the analysis passes. And rollback on health check failures when it is set to true, which enables automatic rollback if any health check fails. So this mechanism also extends to resource auto scaling. So where the system can detect memory or CPU pressure patterns and scale horizontally by adding more pods or by vertically by increasing resource limits, and then return to the baseline when the load normalizes. So this prevents resource exhaustion failures and ensures your applications to handle traffic spikes without any degradation. Now I want to share a real-world case study from the airline industry, specifically focusing on a flight booking system, because this represents one of the most demanding environments where self-healing systems prove their value. So this case study illustrates both the extreme requirements and the dramatic benefits that can be achieved. The challenge facing this airline was multifaceted and unforgiving. First, they had a requirement for a 99.9% uptime, which translates to a maximum of 4.32 minutes of downtime per month. This isn't a soft goal. So, this is a contractual obligation tied to the service level agreements with partners and customers. Second, they needed to handle the peak traffic that could spike to 10 times normal load during holidays and special promotions. So, when customers are mostly likely to be booking travel and when the business generates a significant portion of its annual revenue. Third, the system operates across multiple regions and must handle regional failures gracefully, continuing to serve customers even when the entire data centers become unavailable. And they need to operate in a highly regulated industry where every change must be auditable for compliance purposes, requiring detailed tracking of who made what change, when, and why. So, the traditional approach where they were using before implementation, GitOps was plagued with problems. Manual deployments had to be scheduled during carefully planned maintenance windows, which meant they could only deploy new features or fixes at only specific times, limiting their agility. When problems did occur, rollback procedures took 15 to 20 minutes, which sounds fast but was far too slow given their uptime requirements. Those 15 minutes could represent thousands of failed bookings and frustrated customers. So they also struggled with the configuration drift between regions where manual changes in one region weren't properly replicated to the others, leading to inconsistent behavior and difficult to diagnose issues, which is perhaps like more concerning. And human error during emergency situations was at a constant risk. So when engineers are under pressure to fix a production outage, mistakes happen, and those mistakes can be expensive and can compound more to the actual original problem. So the solution this airline implemented during GitOps principles transformed their operations in fundamental ways, and the results speak for themselves. They implemented multi-region GitOps with a single Git repository serving as the source of truth and multiple ArgoCD instances deployed in each region. So this architecture provided automated regional failover capabilities and eliminated configuration drifts between regions entirely, because every region was continuously reconciling against the same Git repository. So they adopted a blue-green deployment strategy that enabled true zero downtime deployments where the new version is fully deployed alongside the whole old baseline version, and it gets validated thoroughly, and then the actual traffic is switched over instantly. So this approach provided instant rollback capability because if anything goes wrong, you simply switch traffic to the blue environment, which is still running and healthy. So the traffic shifting decisions were based on real-time metrics, not just successful deployment of the pods, but also the actual evidence that the application was performing correctly under production load. The self-healing scenarios they implemented cover a range of common failure modes. They can automatically scale databases, connection pools when pressure is detected, preventing the connection exhaustion issues as we discussed earlier. And they also have auto rollback configured for latency spikes, where if the new version shows increased response time, it automatically roll back before the customers notice the issue. So they implemented an automatic regional traffic routing. So if one region becomes degraded, the traffic is shifted to healthy regions without manual intervention. They even have a memory leak detection that can automatically restart pods when memory usage patterns indicate a leak, and buying time for the engineering team to implement a proper fix. The results achieved were remarkable and exceeded even their ambitious targets. Mean time to recovery was reduced from 20 minutes to 90 seconds, more than a tenfold improvement. Over 6 months of operation, they had zero manual rollbacks, meaning every rollback that was needed was performed automatically by the system faster and more reliably than a human could. So, most impressively, they achieved 99.995% uptime, actually exceeding their already stringent target of 99.99%. which this improvement translated directly to the business value in terms of revenue and customer satisfaction maintained at the highest level. And also focusing on the operational cost reduced by eliminating after our emergency responses. So now let's explore the artificial intelligence, how artificial intelligence and machine learning can enhance self-healing pipelines, taking them from reactive automation to truly predictive and intelligent systems. This represents the cutting edge of where the industry is heading. And while not every organization will implement all of these capabilities immediately, understanding the possibilities helps you to plan your roadmap. Intelligent anomaly detection uses machine learning models that learn the normal patterns of your applications and can also detect anomalies before they turn into incidents. So this goes far beyond simple threshold based alerts, right? For example, the system might learn that your application typically has a subtle increase in your memory usage over time that resets each day. And it can distinguish between its normal pattern from a true memory leak. So if it can identify a subtle memory leak 30 minutes before they would cause an out of memory error, giving the system the time to take preventive action like restarting the pods with the new version ready to take over. So the predictive rollback takes this step further by predicting the probability of failure based on historical patterns. So the system might analyze a new deployment and determine that it has 85% similarity to a previous deployment that failed, perhaps because it changes the same components or had similar performance characteristics. Based on this pattern recognition, it can recommend a rollback before any actual failure occurs, essentially learning from the past mistakes to avoid repeating them. The intelligent canary analysis adjusts the analysis duration dynamically based on traffic patterns rather than using fixed time windows. So, if you're running a canary during unusual traffic conditions, perhaps during a major sale or a traffic spike from a social media, the system can extend the canary phase to collect more data before making a promotion decision. So, this ensures that you have statistically significant data to make informed decisions regardless of when you happen to deploy. So, the root cause analysis capabilities can correlate metrics, logs, and traces automatically when an issue occurs. So, it can generate hypotheses about what went wrong with your confidence scores and suggest specific remediation actions. This dramatically reduces the time engineers spend diagnosing the issues, allowing them to focus on implementing fixes rather than detective work. So, the resource optimization uses historical data to predict resource needs based on deployment characteristics, the time of the day of the week, and other patterns. The system can automatically adjust HPA and VPA parameters to optimize both performance and cost, ensuring you're not over provisioning the resources during low traffic periods or under provisioning during the peak times. So finally, security anomaly detection can identify unusual deployment patterns that might indicate a compromise, or it can flag potential security issues before they are being exploited and automatically block suspicious deployments before they can impact your environment. So this adds an important security layer to your self-healing capabilities as well. So let me walk you through the comprehensive framework for integrating AI-driven intelligence into your deployment pipeline. So this architecture creates a continuous feedback loop that observes, learns, and heals automatically. And understanding how these pieces connect together is essential for the implementation. The first phase is a continuous monitoring phase where we collect metrics, logs, and traces in real time from all the components of the system. So, this includes tracking health checks to ensure pods are responding correctly, monitoring the service level objectives to measure whether we are meeting our reliability objectives, and also observing resource usage patterns and establishing baseline behavior for what normally it will look like in a specific environment. So this baseline is crucial because normal looks different for every application and organization. So the second phase is anomaly detection, where AI and machine learning models compare the current state against the established baseline. This uses both static thresholds for known failure conditions and dynamic pattern recognition for more subtle issues. So the models are continuously learning of what normal looks like and can identify deviations even when they don't cross predefined thresholds. So this catches issues at the traditional alerting might miss. So the third phase is the risk assessment, where the system can calculate the probability of failure based on multiple signals. It determines the severity and the potential impact of the detected anomaly and decides whether to simply monitor the situation, alert the team, or take immediate automated action. So this decision tree prevents alert fatigue from false positives while ensuring real issues that gets immediate attention. So the fourth phase is the automated remediation. When recovery actions are executed, this might include triggering auto rollback through ArgoCD to return to a known good version, dynamically scaling resources up or down to address the capacity issues, or shifting traffic away from problematic instances, or restarting the pods while ensuring that known good images are used. So these actions happen in seconds, far faster than any human could respond. So the fifth phase is the GitOps reconciliation, where the system updates the Git with the remediation actions that were taken, creates a comprehensive audit trail showing exactly what happened and why it happened, and also notifies the team with detailed analysis, including metrics, logs, traces, and recommendations for long-term fixes. So this model ensures that automated actions don't happen in a black box, but they are fully transparent and auditable. So the sixth and the final phase is continuous learning, where the outcomes of all the actions are fed back into the AI models to improve their accuracy over time. The system redefines thresholds and policies based on what works and what doesn't, continuously improvising detection accuracy with each incident. So this creates a virtual cycle where your self-healing capabilities become more effective the longer they run. So as we think about implementing these self-healing systems, there are four core architectural principles that must guide your design decisions. So these principles ensure that the self-healing capabilities are reliable, trustworthy, and continuously improving. The first principle is the continuous loop, creating an unbroken cycle of observe, detect, and then decide, act, and then learn. So this isn't a linear process that ends after remediation. It is a continuous cycle that ensures constant vigilance and ongoing improvement. So the system is always observing, always ready to detect and respond to issues, and always learning from what happens. The second principle is full automation for common failures. So no human intervention should be required for routine issues that the system has seen before. The system responds instantly to known patterns, preventing incidents before they impact the users. So this doesn't mean humans are removed from the loop. It means they are freed from the toil and can focus on more novel problems and strategic improvements rather than fighting the same fires repeatedly. The third principle is complete auditability. So every action must be recorded in Git, and your observability tools create by creating an immutable history for compliance and debugging purposes. So when something happens, you can trace back through the entire chain of events to understand exactly what occurred, what decisions were made, and what actions were taken. So this is crucial not just for compliance, but for building the trust in your self-healing systems. The fourth principle is self-improvement, where AI models learn from each incident and continuously refine their understanding and response capabilities over a period of time. The system doesn't maintain a static set of rules. It evolves based on experience, becoming more accurate and detecting issues more effective as they resolve them as it encounters more scenarios. So, understanding the high level journey from detection to resolution is critical for implementing effective self healing systems. So, let me walk you through the practical steps for building these capabilities in your organization. So, start with observability. because you simply cannot heal what you cannot see, as we discussed earlier. Before automating anything, implement comprehensive metrics collection, log aggregation, and focus more on distributed tracing. Define clear service level objectives and service level indicators that represent what healthy looks like for your applications. Ensure that you have the visibility needed to detect the problems quickly and understand their impact. Many organizations make the mistake of jumping straight into automation without establishing proper observability first. And they end up with the systems that take automated actions based on insufficient information. Move to gradual automation rather than trying to automate everything at once. Begin with a manual approval gate in your pipeline so humans can review each deployment. Add auto rollback or for your most critical services first, where the value is highest and then the stakes are greatest. As your team builds confidence in the automated behaviors and refines the health checks and thresholds, expand the automation to more services. So, this gradual approach prevents automation from making things worse and allows your team to learn and adjust as you go. Test your healing capabilities explicitly using chaos engineering practices and also intentionally inject failures into your system to verify that auto recovery works as expected. So, this might feel uncomfortable at first, breaking things on purpose, but it is far better to discover problems with your self healing pipelines during a controlled test than during a real incident. Practice your instant response procedures during these chaos experiments so the team knows what to expect and how to intervene if needed. Also, maintain human oversight throughout the process thoroughly. And initially, AI should suggest actions and humans should decide whether to take them. Audit all the automated actions to ensure that they are appropriate and they are effective. Also, maintain manual override capability for unexpected scenarios where automated responses might not be appropriate. So, the goal isn't to remove humans from operations, it is to augment human capabilities and allow people to focus on the problems that truly require human judgment and creativity. So, to conclude, let me share some best practices that have proven essential for operational excellence when running self healing pipelines. So, these guidelines come from a real world experience and represent patterns that successfully organizations follow. So, GitOps hygiene is foundational to everything else. Make small, frequent commits rather than large and risky changes. Always have better practice to write clear commit messages that explain not just what changed but why it changed, providing context for the future maintainers. Implement proper branch protection rules so no one can push directly to production branches. And also adjust the rules in your repo to have code review for all the changes, treating infrastructure and configuration with the same rigor you apply to the application code. And these practices might seem like a overhead initially, but they do prevent far more problems than they cause in a longer run. So the progressive delivery practices should be universal rather than optional. And always use canary or blue green deployment strategies, even for services you consider low risk, because you never know when a change will have unexpected consequences. So, start with your low risk services to build confidence and refine your practices, and also monitor closely during early deployments and be prepared to adjust the thresholds based on what you learn. Gradually increase the scope of automation as your team becomes comfortable with the patterns and confident in the health checks. Documentation and runbooks might remain essential even in highly automated environments. So document all self-healing behavior so everyone on the team understand what the system will do automatically and under what conditions. Create detailed runbooks for edge cases that require human intervention. Also share those learnings and insights across teams to so that the knowledge doesn't stay siloed. Maintain up-to-date troubleshooting guides that explain both how to work with the automated systems and how to make a manual control when necessary. And continuous improvement should be baked into your culture and processes. and also review incidents and near misses regularly so that even the ones that were handled automatically to understand if there are deeper issues to address. Tune the AI models based on actual outcomes rather than assumptions. Iterate on thresholds and policies as you gather more data about your specific applications and usage patterns. Conduct what is regular, like regular meetups with the team or like regular retrospectives where the team can discuss what's working, what isn't, and what could be improved. This commitment to ongoing improvement ensures that your self healing capabilities become more effective over time rather than stagnating and getting stuck at a point. I hope this session has given you both information, detailed information, and practical guidance for building the self healing CI/CD pipelines in your own stacks. And I would love to connect with you on LinkedIn to continue this conversation, share ideas and experiences, and support each other as we all work toward more resilient, reliable systems. Let's stay connected and stay in touch and learn from each other's journey. That's my time. Thank you for your time today, and Conf42 for this. Thank you, Conf42, for this excellent opportunity to share my experiences with the DevOps community. Cheers.